Hey y'all, in today's video we're going to look at a property that comes out of the understanding that molecules exist in three-dimensional structures, and we're going to assess the polarity of molecules. Now you might have learned earlier in your career that there are some molecules which are polar and others that are nonpolar, and today we're going to explore that using domain geometry, bond geometry, and our understanding of electronegativity. So let's remember initially that more electronegative atoms have greater effective nuclear charges and are generally smaller due to fewer energy levels. That's based on Coulomb's law. When we're looking at molecules, though, we can take that knowledge and apply it looking at molecules and their polarities overall. So let's look at a molecule first of all, and then make a quick change to the molecule and see what effects it has on the polarity of the molecule. So we're going to start with methane, CH4. And then we're going to replace in this molecule two of the hydrogens with two fluorines. Polarity of a molecule is all about the symmetry of the electron cloud. If the electron cloud is symmetrical, then what we're going to see is a nonpolar molecule. And if the electron cloud is asymmetrical, all right, so uneven, we're going to see a polar electron or a polar molecule due to its uneven electron cloud. Now, when we're looking at electron cloud polarity, we have to think about this in terms of three dimensions, but we can look at each bond individually. So each bond within the CH4 is essentially the same thing. So if we look at each bond within the CH4, it is essentially nonpolar because of the fact that carbon and hydrogen have very similar electronegativities. So those atoms don't really pull on electrons any greater than each other. And so we end up with a molecule three-dimensionally that looks like this, but the electron cloud is fairly symmetrical around this molecule. That's nonpolar. The second we replace two of those hydrogens, though, with fluorine, fluorine is a much more electronegative atom. Now, if I look at the diagram, it looks symmetrical. It looks like the fluorines would cancel each other out. But the thing is, when we look at this in three dimensions, you can see they don't. The fluorines are not directly across from each other in three dimensions. Neither are their hydrogens. So instead, what's going to happen is we're going to see a very dramatic asymmetry of the electron cloud. Way more electrons are going to be existing down here near the fluorines, and way fewer electrons are going to be up here near the hydrogens. This creates what's called a dipole moment. Okay, a dipole moment. Dipole moment is basically saying it's a dipole that exists permanently. All right. So if we have a dipole moment, in this case, the partially negative charge, the negative dipole, is going to exist near the fluorines, and the positive dipole is going to exist near the hydrogens. Fewer electrons near the hydrogens, more electrons near the fluorine. Now, if we were to diagram this, we wouldn't be able to necessarily do it well with the two-dimensional model. Because again, when we look at the bonds, I'm going to show you a dipole here in the fluorine. It sure looks like those two just cancel each other out. All right, so the fluorine-carbon single bonds are very polar. Fluorine is a much more electronegative atom than carbon, but overall it creates a polar molecule. This is one of the reasons that we always need to think about molecules in three dimensions, because when we're assessing the overall polarity of molecules, that's the most important element. Okay, we need to make sure that it is three-dimensional in our heads. That way we can apply it appropriately to understand that this is a polar molecule. The other thing to keep in mind when we're looking at polarity of molecules is that it's not always just about bonds and the atoms and the ligands, but also about lone pairs. So if I'm looking at ammonia, remember there's a lone pair on the nitrogen. That lone pair on the nitrogen is going to make the overall molecule look like this. Now, lone pairs have very high electron densities, relatively speaking. I mean, they are lone pairs of electrons. So in this case, there's going to be a negative dipole associated with the nitrogen and positive dipole associated with the hydrogens. Okay, so in other words, we have created a dipole moment because of a lone pair. This again creates an asymmetrical distribution of the electron cloud. More electron density near the nitrogen, less electron density near the hydrogens. This is a polar molecule for that reason. Okay, so we've assessed now using atoms. We've assessed now using lone pairs. Let's take a look at a couple more molecules and take a look at what it looks like to have either being a polar molecule or a nonpolar molecule. Carbon dioxide is the next one we're going to look at. Carbon dioxide, remember, a carbon double bound to two oxygens, 180 degree bond angle. In this case, both bonds are very polar. All right, oxygen is much more electronegative than the carbon. When I draw a polar bond, remember, I'm going to draw a dipole such as this. All right, so the oxygens are pulling away electrons, as it were, due to their high electronegativities. But in this case, they're pulling equally away. And because of that, their pulls essentially cancel out. And so we end up with a symmetrical electron cloud around the carbon atom. Therefore, this is a nonpolar molecule. Nonpolar because the vectors of your electron domains cancel out compared to otherwise where they wouldn't. So this carbon dioxide is a nonpolar molecule. Now let's modify carbon dioxide a bit. We're going to turn it into carbon monoxide right now and take a look at the configuration, the Lewis structure, but also its polarity. When we're looking at carbon monoxide, the oxygen has a fully unchecked pull on electrons. So in carbon dioxide, you can see the two oxygens pull equally on both sides. Carbon monoxide, that's not the case. The oxygen is pulling on the electron cloud. So we end up with an asymmetrical electron cloud in this case, where there's going to be a negative dipole on the oxygen. I'm going to show that using this lowercase delta sign with a negative, and there's going to be a partial positive charge on the carbon. So a dipole moment is a permanent dipole created by an uneven sharing of the electrons in an electron cloud due to changes in either the geometry, structure, and shape of a molecule, or based off of the atoms, the ligands around a central atom. So there are a lot of things that can create a polarity of a molecule, and it's going to be your job to recognize and understand a molecule that is polar versus nonpolar. But in general, if you have lone pairs, it's much more likely that the molecule is going to be polar. If you have non-equal numbers of atoms around the central atom, so for instance, in the CH2F2, right, you had two hydrogens and two fluorines, that's a big key to that molecule being polar as well. So when we're looking at polarity, we're looking at asymmetry of the electron cloud. And if you're ever going to describe something as polar or nonpolar, the way you do it is by referencing the relative symmetry of the overall electron cloud around the central atom. So that's the end of this video. Today we looked at how to determine relative polarity of molecules using our understanding of electronegativity, electron domain geometry and shape of molecules, and then we applied it by understanding that three-dimensionally electrons around a central atom may or may not be symmetrical around that central atom. If they're symmetrical, it's a nonpolar molecule. If they're asymmetrical, it's a polar molecule. So I hope you enjoyed this video. I'll see you in the next one.